I'll be talking today about developing template code, and one of the things about template code that fascinates me, almost since I started learning to program, I've been interested in metaprogramming. I guess as a programmer, I'm a domain expert in that, like all of you. And so writing programs that write programs is something that I feel I can be of benefit for it too, and make some contribution. But since coming back to C++ a few years ago, I've read lots of books on template programming. There's this wonderful book here, 800 pages long. We've got, and I've looked at lots of talks, but almost none of the talks that are out there, none of the books give any information on actually developing template code. I mean, yes, the template book here has 11 pages in it out of 800 that talk about debugging template code. And you'll see occasionally you get tips in talks where the speaker makes some useful suggestion, but that's it. So what this talk is going to do is to gather all of these known techniques, known tools, and present them to you. And you'll probably know quite a few of them, but I hope that some of them are new and some of them will be used by yourselves in your everyday development. So one thing that Conor Hoekstra, who is incredibly fluent and does these wonderful talks and has brilliant videos, what he doesn't have is he doesn't have alpacas. I have alpacas. So, and you'll be seeing some of my alpacas in the course of this talk, but we won't talk about them too much. So what are we going to look at? We're going to look first at basically the coding life cycle. So we'll look at compiling. How do you get your code, the blasted code, to compile? Because often that's not as simple as it should be. And we'll also look at debugging it, and sometimes that's debugging before it can compile. Sometimes it's debugging after it compiles. We look at testing it, and finally we look at making it better, making it faster to compile, making it faster to run, and we look at some of the specific benchmarking tools that are used when you're developing template code. So my name is Jonathan O'Connor. I work for a small German company, the Cluster Company. I live in Ireland, but pre-COVID, I was in Germany an awful lot, and that's why I was able to visit Jens and the Düsseldorf C++ meetup group regularly. I've been metaprogramming since 1983, and I actually wrote my first metaprogram on this machine here. It has 3.5K of RAM, and I got it to renumber a basic program. That was the extent of it. And then I learned Lisp in college and did lots of metaprogramming there. And I've done stuff in C++, Java, and Ruby, and basically any language that I get hold of. If I get deep enough into it, I want to write metaprograms. And apart from that, I play a lot of chess and I make ice cream. And you can find me on Twitter, is probably the easiest place to get me. At Ninkiba is my handle, and my GitHub account has the same name. So this is what alpacas do when they're waiting for compile to finish. They just sit around and relax and enjoy themselves. So it's probably a good idea for all of us. So we're going to look now at compiling our code. And as Timur yesterday, he mentioned that you get long compiler error messages, and you get loads of them. And like, one of the problems is that unless you have very, very wide screens, one of these new, like, I don't know, they're like a meter wide, curved and everything, you can never read to the end, and you have to scroll right. And who scrolls right? Nobody scrolls right. We all scroll down. So that's a problem. So what are you supposed to do? I was writing some code a few years ago, and I had created a set of ints or whatever, something else actually, but and that was fine. And then I'd read or I'd seen a talk by John Lacoste, and I thought, oh yeah, that's great. I want to drink his Kool-Aid. So I thought, okay, I'm going to add an allocator in there. And I put in this allocator, and I compiled my code, or so I thought, and I got all of this. And I thought, oh hell. And when I see that, I don't know about you people, but my brain just shuts down, and it's totally overloaded. I can't take all that text in. I don't know where to look. And so my first suggestion to you all and to myself is take a deep breath and then start reading the error messages. And in preparation for this talk this morning, when I was looking at this slide, I noticed if I had read it carefully, it would have been obvious to me where the problem is. I think, yeah. So you can see it's having a problem with comparisons. And here it says key comparison, and it says no match for call stud allocator int. So there's something to do with allocator and comparison. And that's what I could have learned if I'd looked at this from the word go. And then my other suggestion to you is do scroll right, do read to the end. And I've had to reformat this. But if you go to the very end of this, these lines, you often get told the deduce types that are being used in the type declaration here. And we can see here that that we've got, sorry, my mouse there. We have the compare template argument is actually an allocator. And that sounds wrong even to me. So that was my problem. My problem was that I had forgotten to specify a comparison function. And the reason I didn't do that was that I thought I could get away with allowing it to provide the default value. But unfortunately, the comparison template parameter for sets is the second template parameter and not the third, which the allocator is. So that's why I was getting all these errors. So that's my problem. So the second, when I was told I was giving this talk, I asked for help on Twitter, and I got lots of great suggestions. And Ben Dean, he told me a trick that he uses is that he copies the type declaration out of the error message that he gets, and he sticks it into his editor, and then he uses Clang format to reformat it. And that often, he says, makes it easier to read. And I tried it on this, and I don't really like this. It may be, I mean, I don't think it's much better than what. Yeah, I don't like the formatting that it does, and maybe it depends on the code you've got, but that's yeah, it's not wonderful. So another suggestion I got was Vittorio Romeo. He developed a Python script called Camomilla. And actually, I'm just wondering, is superv1234 his password? But anyway, to go on, his script, what it does is you pipe all the error messages into it, and it goes around and it replaces the namespaces and long type names with shorter versions, or it can throw away namespaces as well. And so you can do things like you can get it to they'll throw away STD everywhere. it could probably change basics underscore string to string, but it won't change stud colon basic string less than char greater than with just the type string. And that may be a shortcoming in it. But here's some examples of it. So he has a sample in the README where he has this big long type of nested template types, and he throws it into he pipes it into CppInsights with a parameter of D0. That's the depth of replacement that it's going to do. And 0 means, well, only don't bother replacing, just give me the top level types. And this outputs metavector ? ::x. So it certainly cuts down on all of the strings. It reduces them to a large extent. And here's another example where we have a vector of a pair of two different types of ints. And when you pipe this through CppInsights with like infinite depth 100, I hope you never have templates that are deeper than 100. You end up with, it spits out just vector pair int 16, int 32, which is a lot shorter. And in some of his tests that he's done, he has gone from he's gone down to like 10% of the original error message size, which is pretty good. And his tool can be configured with your own application-specific, project-specific namespaces and types, which means that you can really reduce your error messages a lot. And once they're down to, like, if they're 10% of the original size, then you don't have to panic as much, and it's easier to read them. So that's compiling and tricks to use for compiling. And now we're going to go on to trying to debug our code. So the template, one of the things about template debugging is, don't forget, you can still run your code through a normal debugger. That's if it compiles. And that's especially true of const_expr functions. You can step through those, which is quite nice. If you can't do that, and often it's a problem to figure out what types you're dealing with at any stage in your program. And as template code has often loads of stuff to do with types and deduce types, it would be nice to be able to print the type name. And we're going to look at 3 different ways to do that. We're going to look at a way to do it at runtime, if you want to spit it out in error messages or log messages. And we're going to look at 2 ways of doing it at compile time. And then we're going to look at template instantiation tools. And there are a few of them out there. Some of them that you know and some of them that you probably don't know. So the first thing, here's a quick example of our debugging a const_expr function. And we've got it, this is just some of my own code using cline, and underneath the hood it uses GDB. And you can see the types and the templated types, and as you step through it, you can see, so you can get type information from your debugger, so long as your code is compilable. So now we're going to look at, like, if you need to find out what type you've got, what the deduced type of something is. Well, C++ already has a reflection, some reflection built in, and it's been there for a long time. And you can use this type ID operator, and then this gives you a type info object, and then you can ask for its name. And if you do that, you get this. And I'll let you guess what that is, what the T in this case is, but it's not really pretty, and it's, we don't want to go there. So that's not an option. Another thing is that all compilers have this function built in, underscore underscore function underscore underscore. And what this returns is a const char star to the name of the function that's running. That's where this function appears, and this could possibly be a way of finding out if we had the right type of function, we might be able to get our type name in a nice way. But unfortunately, at least on GCC, it doesn't show templated arguments. So that's not an option, but there is a nicer one again, which is pretty function. And on GCC and Clang, this actually will show the whole function plus the template types. And that's great. It doesn't work on Microsoft Visual MSVC. And maybe MSVC has something similar. You could ask Cy Brand or Victor Chura, or probably do a Google search. But yeah, so we'll have a look at taking advantage of these. So pretty function here, if you have a print me function, and if we see out pretty function inside that, what we end up with is it prints out void print me int. And so it tells you everything you want to know. And if we do it on a templated function, here, yeah, when you do that, it prints, and you call print me int. It shows this, and this is the important thing. At the end of the print me, it specifies what the template arguments are being replaced with. So we get with t equals int. And so if we can extract the int bit there after the equal sign, then we're good to go. And just one other thing. I use GCC as my standard compiler, so I never use Microsoft VC, and I don't use Clang. But I did try to run this thanks to Godbolt, and I found that in Clang it'll only expand the template arguments if they're used as function arguments. So I've stuck this t star equals null pointer in there as an argument to the function, and that will ensure that t equals whatever it is will come out in the expansion of pretty function. So from that, we can write our own function to print the type, and this function here, if you can actually stick a const expr onto it if you're running in GCC 10.2. Clang 11 hasn't come up to date yet with that, but in C++ 20, const expr strings are allowed, and that's pretty nice. So we create a string from a pretty function. We look for the equals inside it, and we should always find it because we're inside a template function, name of t. And so this should never happen. And here we just extract a substring from 2 characters after the equals, and we take it up to the character before the right bracket, just to show you what it looks like there. Yeah, so there we go. So from the equal sign to the right bracket, that's what we're extracting. And when we run this in GCC, it prints out stud : whatever basic string. And in Clang, different standard library implementation. So, but it's putting in these underscore CXX11. I think that's the fearful ABI that people keep talking about in the standards committee. So that's doing it at runtime. But what happens if your code doesn't compile? You may want to figure out what your deduced type is before the point of failure. And Ivan Chukic author of this very nice book. And whoops, there we go. Functional programming in C++. He gives it a nice tip to be able to print a deduce type at compile time. And what he does is that he has a template struct declaration, but he doesn't give any definition. So he has no implementation for it. And when you instantiate such a beast, it causes an error. And in the error message, you'll see the type that caused it. Now, the downside is that it generates an error and it stops compilation, and it's much of a muchness. So this is what it looks like. We have our declared struct here, print me as error, but we have no definition for it. So we have no implementation. And when we instantiate that with some type here, print me as error and stud vector int : element type. So what is the element type in an int vector? And you'll get an error message at that point. And it'll say error, invalid use of incomplete type. And then you'll see there it says class print me as error int. So it's actually figured out what the deduce type is of that element type, and it displays that to you. And so it does the job, and now you know the exact type that may or may not be relevant to your problem that occurs further on in your code. Another way of doing that is, it was told to me by a friend of mine, Daniel Fry, who also visits the Dusseldorf meetup, and he's also one of the co-authors, along with Colin Hirsch, of the Tau CPP library. And what he does is he generates a deprecated message, and he has a templated variable, Boolean variable, marked as deprecated. And when you instantiate that, you get a deprecated warning. And how we normally how you instantiate it is that you stick it in as a static assert. So we generate a warning. Okay. So here's the actual code. It's very short, very simple. We have a template on a type, and we have a const expr bool print type, and we set to true because we don't want the compilation to stop when we use it in a static assert, but we do mark it as deprecated. And when you use this, and here we go, we have our big long expression and type declaration here, stud vector int element type. And then what it is, when we run the compiler, it tells us warning, print type int is deprecated, and it gives us the full expression. So it actually gives more information than the previous version, which generates an error, because it shows us both the deduce type and what it's coming from. Okay, so now we go on to some of the tools that are available for figuring out what's going on in your code, what's being generated by your templated code. And there's a fantastic website called CppInsights.io by Andreas Fertig. I think it came out about a year and a half ago or so. And again, it's similar in style to Godbolt that everybody uses. It's actually, it's one of the websites that's in the Godbolt family, so to speak, because, and what it does is it generates C++ instead of assembler. And as assembler is a bit difficult to read, but we all read C++. And this doesn't just copy your code from one window to another. It actually generates a simpler version of your code, and it shows you what the compiler is generating. I think how it works, it uses Clang under the hood, and it takes the AST tree, and from the AST tree, it regenerates C++ from it. And one of the things that the classic use cases was to show how your range-based for loops actually, what code they actually create under the hood. But for us, much more useful use case is it shows the template instantiations. And that's really what we need. So here is some code. I'll be looking at this code later on, but on the left, you see my actual code here. And I have a templated function called downgrade, and it takes advantage of, it uses if const exprs to do clever things depending on my version number and what's possible with my person class. And on the right-hand side, you'll see that inside the #ifdef insights use template, you'll see that the code insights has expanded my code and instantiated it and generated the code that's actually going to appear in each instantiation of this function. So the first version shows an instantiation of the downgrade function when n is 1, and the next one shows it when n is 0. And you can see that in each case, in both cases, the static assert has disappeared because it's not relevant. And in the top case, the condition 1 greater than 0 is going to be true, and so the code it calls current.downgrade, calls downgrade on current.downgrade. Okay. Anyway, that's an error in the downgrade. I'm thinking of my old code. Apologies. So that's one tool. There's a second tool that helps you to debug your template code. This is a tool that I think hasn't received a lot of attention, and I think the reason for that is it's difficult to. You have to know a lot about to get it to run, and you have to know a lot to actually use it. So there's a steep learning curve, and I didn't actually get it to work when I tried it. But it's called Metashell, and it's basically, it allows you to, it's a meta debugger. It allows you to debug the compiler as it's compiling your code. And you can set breakpoints when certain actions occur. So I would love if somebody could come up with a web front end like Godbolt, like CPP Code Insights. That'd be fantastic. Somebody did come up with so this is what it looks like. Metashell. This is some of their documentation, and they do have a demo version that runs, but it only allows you can select between C++11 and C++14, and I'm not sure how to use it. My code is C++20, so it wasn't going anywhere. But there is a front end for it called a Qt front end called Metashell GUI, and it can be found here on GitHub. And I think it looks fantastic. And if I could use this on my code, I would. As you can see here, they have a Fibonacci template function, a meta function, and you can see on the lower right part of the screen, you can see that you get template instantiations for the different Fibonacci types, and then it also shows you when it's already cached one of these types, and so you've got memoization there. I don't know if you can read that, but I think that's a really cool tool, and I'd love to be able to use it for my own work. So that's debugging. Now that we've got our code compiling, we can start running with it and testing it. And the first thing to remember is that you can always run your template. You can always write tests for your template code that run in your standard test framework like Catch or Google Test or whatever. So here's a simple constexpr template function to double whatever it gets, and we can write our test case just like we do with all our usual test code. So that's standard enough. And then you've got your compile time tests. So sometimes you actually want to test stuff at compile time and to stop the build if your tests fail. And so this is all based on the static assert keyword or function that's in the language. I'm sure you all know it. It goes back quite a long way. It's probably, it comes from definitely the Boost static assertion library. These two people, Robert Clower and John Maddock, proposed it. It was the first thing that was introduced into C++11 standard using the static assert keyword. And you take a Boolean expression and some error text. And if the Boolean expression is false, then the compiler stops with an error and it displays the error text. And in C++17, they added, they threw away, they made the error text optional. And that was probably because a lot of people were giving the Boolean expression and they were repeating the Boolean expression in the error text. So there was a duplication and wasn't really necessary. So that's gone. So here's a very easy, simple sample. Static assert false, and this will generate an error with the text whoops in it. So you all know that. And so again, here we can put in our static assert. We could have an immediate test there, and if this ever failed, our code wouldn't build. And we could go and fix it immediately and before even checking in the code or whatever. So then the thing is, like, when do you want to use this? And I've used it in two different places, static asserts. One, I've used it to when I've declared various types, classes, structs, and I want to make sure that they have a certain qualities, certain traits, to coin a word. So I might want to make sure that my some struct is always movable and copyable, and I could put in a static assert to that effect immediately after the declaration, and then if one of my colleagues or myself changes that at some stage later and stops it being movable or copyable or whatever other characteristic I want, the compile will fail immediately, and we'll know what the problem is, and that's a useful way of using it. And the other time I use it is in if constexprs statements, normally for the else branch, when I've passed something into a type into the function that I don't know how to handle, and at that point I want to generate an error message, and this will generate closer to the point of call, and it should be smaller and easier to understand. So that's something useful. So here's my example from before, and with further explanation. So in my in-memory database that I've been working on, we allow for versioned data. So you can have like a person struct, and you can have the initial version of it, and then as your program, as the application develops and changes over time, we need to add in new fields, we need to rename fields, we need to delete fields. But we have old data hanging around on disk, so we want to still be able to read that. And so you have to create a new version of the person each time. So we have our person struct. It's a template type with a templated on a version number, and our initial version, person 0, just has a first name and last name, and our person 1 has both a first name, last name, and a year of birth. And for our purposes, we'll add a migrate down function, which takes the data in our person 1 and generates the previous version, an instance of the previous version of the person from it. And we can use that in our templated, on our context for function that we had. So here's our downgrade once function. So we take our person n, reference to it, and if we have if n is 0 at compile time, then we just return. We can't downgrade any further, so we just return the object or a copy of the object. If our person class has a migrate down function, and this is using this neat C++20 syntax that was described recently by Jason Turner in one of his videos on YouTube. So this will only get invoked if our class has a migrate down function, and so we just call it. And if it doesn't, then we're going to generate an error with our static assert. And this looks great because this else block will only get invoked when n isn't equal to 0 and when our person class doesn't have a migrate down function. But unfortunately, because of the false there, the compiler sees false and says, oh, that's false, I have to generate an error message immediately. And it does that, and that's not very useful. So there's a fix. We want to get the compiler to delay expanding that, delay checking that value. And you can do that with this trick called the always false template. And because we have we have what is it? It's a templated variable here, which happens to always generate a false value. But because that's a template, an instantiation of a template, the compiler can't figure out what it is just immediately, and it'll only figure out what that value is when it actually needs to generate this else clause. And this trick has been used. It's been used. There's an example of it I came across in the CPP reference under the variant visit sample code. There's a description of it's used there to do exactly the same thing, to find out when you've got a what is it? Oh, I've forgotten it. Sorry. But always false here. It's a template variable. Its value is always false, but the compiler only figures that out when it instantiates the particular version, and that won't happen if you've got n equals 0 or your type has a migrate down function. So that's a useful thing. So the next trick we can use in testing is we can test to see if our templated code is using the minimal amount of functionality to allow for the maximum number of types that will apply to our code. And archetypes are one of the things that are described in the 11 pages of the C++ template book. And they're there to, you create a test class that has minimal behavior. And you use that as your template parameter to your code. So it's also mentioned by David Abrahams and Douglas Gregor, and these two people were the guys that created Swift, according to, well, I know we were told that yesterday in Connor's talk. And there's a link here to, this is one of the oldest web pages on C++ that's out there. It dates back to about 2000, 2001. So many of the older pages are getting lost. And anyway, The other thing about archetypes is that if you're using C++20 concepts and you're labeling your template parameters with those concepts, you're going to have less need to create these archetype test classes. But you may, if you have your own special concepts, not standard concepts as are defined in the concepts header, then you can use the same this archetype testing technique there. And there's 3 great articles written recently by Andrzej Kremensky. Apologies for that RZ is incredibly difficult for me to pronounce. But he's I guess a Polish developer, and he has a blog where recently, it's in September and October, he wrote 3 articles on concept archetypes and an update, and finally semantic requirements and concepts. And he has really great description of what archetypes are and how they're used, and how you go about creating them and modifying them to improve your template code. So I'm just going to show you what was given in the in the templates book in some of those 11 pages. You end up writing really small classes, and you often delete functionality. So the template book has an example of a find function that takes an array of any type of object, and it takes the size of the array, and it takes a reference to a value that we want to search for. And the idea of this is that it should return the index of the position where the value is found inside the array. And if you don't find it, then it returns the size of the array, n here. So we have a small little bit of code. We have a small bit of code here. We loop around over the array, and we check if the ith element of array is not equal to the value, then we increment I, and eventually we come out of this loop and we return I, either at the position or we return the size of the array. So how we go about testing this is first of all, we create an archetype class. And this, we know we've got to be able to, our type has to be comparable, and it has to be comparable just for equality. So we create an equality comparable archetype. In fact, like, this is one of the standard concepts in C++20 that you get. I can't remember what the exact name is, but you can look it up. But there's definitely a concept now for checking that something is equality comparable. And our type, as you can see, has no data in it. There's no functions in it. But we need to define a Boolean equals operator. And that's what we can do. So when we do that, that gives us our first test. But the equality operator, maybe it doesn't have to return bool. That's not a given. So we might want to change that, and we might want to make some kind of archetype for our Boolean type. And so here we have, and this is what the book shows, you have a convertible to bool archetype that just has a conversion operator to Boolean. And our equals operator then produces one of those instead. So you can see we're kind of paring back to absolute minimum dependency. We don't want to we want to be able to handle all types, as many types as possible, and using these archetypes helps to both document and test our implementation. So now, if we create an instantiation of our find function with equality comparable archetype, and you can do it just by typing template in and then giving the special type, the compiler will generate an error. And what it doesn't like here is it doesn't like the not equals. This is having taken that lesson, taken the deep breath, and read the error message. It's obvious what the problem is here, that we cannot do not equals comparison between our equality comparable archetypes. So we'd have to change our code, and that's relatively simple to do. We can just use equality, the equals operator, to compare the two values, and we can use the not operator on that. And the book goes into further examples where you can go further and improve the code to rely on, to have less dependency on stuff. So, but I'm not going to do that here. So that's it for testing. How are we doing for time? Okay, 10 minutes, right. So we're going to look now at ways of making our code lean and mean, and we're going to look at it, making it better. So benchmarking. So part of the benchmarking, we're going to look at two different ways of doing it. One with some C++ code, and one with various tools to figure out our build times. So there's another section in the template book on tracers. And tracers are ways of counting the number of times a particular templated function is called, no, a particular function is called inside your template on an instance of a template parameter. It's described in chapter 28 here, and it normally is used to test how many times particular constructors and destructors are called. And I found an example of this in libstud C++, and unfortunately, I just found it one day while I was working on some other code, and I forgot to make a note of where it was. Now I can't find it, but it looks basically like this. So we have a traced item. This is a test class, and you keep an account, a static count of all the constructors. Whenever a constructor is invoked, we increment one of these static counts. So we have default constructors, we have copy constructors, move constructors, and in our default constructor, we increment the default constructors count. And in the copy constructor, we do the same on the copy constructors count, and the same for the move constructor. And then if we use that, we can test. Here's a test on a stud vector of a traced item, and if we run in place back, and if we look to see what our counts are, we find that in place back makes a single call to the default constructor, and that's it, because takes no arguments, and we have that will invoke the default constructor of our traced item. If you want to use pushback, we can pass in traced item, and we have to use a default constructor to create the argument to pushback, and then inside, because this is an R value, temporary, pushback can use move semantics, and it just does a single move. It calls a move as well. And in place back, you don't want to do this, because if you're using in place back for a default constructible object, then you're doing one too many constructors. But anyway, this is just to show how it works. And in this situation, yeah, no copy constructors are harmed in making this example. So now we move on to the final set of tools, comparing build times. And this is, with templated code, it's easy to sit around waiting for compiles for minutes, even hours, possibly days if your code base is big enough. And so you want to avoid this. And there are lots of articles out there that talk about using fold expressions and all sorts of tricks and techniques to avoid that. But how do you know how long the thing is taking? Well, there are compiler flags. There are also various tools, like there's one from Microsoft here. There's buildbench.com, and there's the MetaBench tool from Louis Dion. So you can use the -ftime -report flag on GCC and Clang. And that's, yeah, there's some useful information. I found there were 3 pieces of information on template instantiation, constant expression evaluation, and constraint satisfaction. And they will tell you how much time is being taken by the compiler. But it's, yeah, it's for specialists, I think. It's for the compiler developers themselves to test out how good their compilation is going. It's difficult to use. And then there's a similar flag to calculate how much memory has been using in the compiler. Again, there seemed to be less useful information in this than the time report. Then there's this Microsoft CppInsights. This is a new tool they've introduced in Microsoft Visual Studio, I think. I don't use it. Talk to somebody who does. It looks a great tool for finding out how long particular pieces of code are taking to be compiled. And you can certainly dig deep down into your system, into the compilation, and see where the time is going. There's a really nice website, buildbench.com, and that's something that I've used a little bit. It was developed by Fred Tingo, and Fred, he's in the Godbolt family of websites, and you can, if you have your code in Godbolt, you can click a button and you'll jump straight to BuildBench with all your code already there. What it does is it allows you to compare 2 or more versions of your application. Now, it should be a fairly short application. It's really only to test small pieces of code. It's not to do your, thousands and thousands of lines of code. When you run it, it compares the length of time and the memory, and it produces a nice graph. So this is what it looks like. So you see on the left-hand side, you see you can see there are 2 tabs, and each tab has a version of this code, different way of implementing it. On the right-hand side, you see how long it took to compile these 2 versions. And obviously, the hand-rolled version, it seems to be much more efficient than the unique sort and using sort and unique version. But so this is sort and unique. I'm not going to go into the code. We're running out of time. Hand-rolled is a different implementation, and there's our graph. And you can also find out how much memory it's using. It'll show that as well in a different graph. But that's almost it. So MetaBench, very, very quickly, fantastic tool by Louis Dion, one of the gods of metaprogramming in C++. You time different versions of your program. It uses Ruby, the only tool that I know of in the C++ world that uses Ruby. Odin Holmes thinks it's the best tool out there for template metaprogramming, and he loves Louis, obviously, with the hearts. You can look at in his website on GitHub. I'm not going to go through all this because we're running out of time. But you get a nice chart. You do need to know a little bit of Ruby, but because the files that you use are called ERB files or embedded Ruby files. There's enough documentation though that out there that, and you need to know very little Ruby to get this to actually work. So I'm just going to spacebar through this. And there's a diagram. Unfortunately, when I tried testing, I failed to get it to work with C++20. My CMake knowledge is not sufficient to do that, but it says in the documentation that you should be able to configure your CMake to use C++ 20 or whatever version. So finally, we are coming to the end now, and conclusions: compiling, read the error message, or use one of these other tools to help you get there. Debugging, printing a deduce type is a really useful trick. CppInsights, great website. Metashell could be fantastic, but it's hard to get working. And then Archetypes, not as useful now that we've got concepts in the language. Benchmarking, we've seen all their tracer types. We've seen compile time flags, not great, but build bench and metabench are really fantastic tools. And finally, I almost forgot Stack Overflow. If you don't have any time to, if you still can't figure out what's going on, Stack Overflow is good. Recently, I joined the Hash Include Discord server and asked questions on the metaprogramming part there, and I got fantastic answers. Thanks very much to Sarah and Seth and Ben, not Ben Dean, different Ben, but they're really nice people there, and they give you great advice. It's wonderful. And of course, Godbolt. I almost forgot. Whenever I'm developing template code, I stick my small little examples into Godbolt and I compile there because it's so much quicker than doing it from C-line or whatever. I'm not sure why that is, but maybe it's because you only look at a tiny amount. So that's it. You can guess which of these guys I am at this stage. Thanks very much for listening. Hope you enjoyed the talk.